Hello, welcome to the video lecture series on digital image processing, and we have said that these transformations are very useful to understand the image formation process. So, in the last class what we had talked about is the basic transformations, and we have talked about the transformations like translation, rotation and scaling, and these transformations we have said both in the 2-dimension and 3-dimensional cases. Then for all these transformations we have also seen what is the corresponding inverse transformation. Then after that we have gone for the conversion from the Cartesian coordinate system to homogeneous coordinate system, and we have seen the use of homogeneous coordinate system in perspective transformation, where perspective transformation we have said is an approximation of the imaging process. So, that when a camera takes the image of a point in a 3-dimensional world, then this imaging transformation can be approximated by the perspective transformation that we have discussed in the last class. Today, we will talk about the inverse perspective transformation. We have said that the perspective transformation takes an image of a point or a set of points in the 3-dimensional world, and these points are mapped to the imaging plane, which is a 2-dimensional plane. The inverse perspective transformation just does the reverse process, that is, given a point in the imaging plane, we will see that using this inverse perspective transformation, whether it is possible to find out that what is the point in the 3-dimensional coordinate system to which this particular image point corresponds. Then we will also talk about the imaging geometry, where the world coordinate system and the camera coordinate system are not aligned. You try to remember that in the last class, the imaging geometry that we had considered, there we have assumed that the 3-dimensional world coordinate system is aligned with the camera coordinate system. That is, x axis of the camera is aligned with the x axis of the 3D world, y axis of the camera is aligned with the y axis of the 3D world, and z axis of the camera is also aligned with the z axis of the 3D world. In addition to that, the origin of the camera coordinate system also coincides with the origin of the image coordinate system. In today's lecture, we will take a generalized imaging model, where the camera coordinate system and the 3D world coordinate system, they are not aligned, and which is a general situation. Then we will try to see that what are the transformations which are involved in such a generalized imaging setup, which will help us to understand the image formation process in a generalized setup. Then we will illustrate this concept with the help of an example. Now, let us briefly recapitulate what we had done in the last class. Now, this figure shows the imaging geometry that we had considered, where the 3D world coordinate system is aligned with the camera coordinate system. There we have taken a 3D point whose coordinates are given by x, y, z, all in the capital, and x, y lowercase coordinates are the corresponding image point in the imaging plane. And we have assumed that the focal length of the camera is lambda. That means, the coordinate of the focal point of the lens center is 0, 0, lambda. Now, using this particular figure, we have tried to find out a relation between the 3D world coordinate x, y, z and the corresponding image point, which is x, y. For that, what we have done is, we have taken a conversion from the Cartesian coordinate system to a homogeneous coordinate system. So, while doing this conversion, what we have done is, every component of the coordinate, that is x, y, z, is multiplied by a non-zero arbitrary constant k, and the same value of k is appended with the 3 components. So, in the for a Cartesian coordinate x, y, z, the corresponding homogeneous coordinate is given by k x, k y, k z and z. So, for a world coordinate point x, y, z, once we have the corresponding homogeneous coordinate k x, k y, k z and k, then we found that after this conversion, if we define a perspective transformation. So, this perspective transformation matrix P, which in this case is 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 minus 1 upon lambda 1, and the homogeneous coordinate W h is transformed with this perspective transformation matrix P, then what we get is the homogeneous coordinate of the camera point to which this world point W will be mapped, and the homogeneous coordinate of the camera point of the image point after the perspective transformation is obtained as k x, k y, k z minus k z by lambda plus k. And you will see that if I convert this homogeneous camera point, the homogeneous image point into the corresponding Cartesian coordinate, then this conversion gives us the Cartesian coordinates of the image point as x, y, z equal to lambda x divided by lambda minus z, lambda y divided by lambda minus z and lambda z divided by lambda minus z. So, you just note that x, y, z in the lowercase letters, these indicate the camera coordinate, the image coordinate, whereas x, y, z in the capital form, this represents the coordinate in the 3D world of or the 3D coordinate of the world point W. Now, what we are interested in is the camera coordinate x and y. At this moment, we are not interested in the image coordinate z. So, this can be obtained by simple conversion, that if we find out the value of lowercase z with respect to lambda and capital Z, then after solving the same equations, here, that is lowercase x, lowercase y and lowercase z, we find that the image coordinate x and y in terms of the 3D coordinate capital X and capital Z is given by x equal to lambda x divided by lambda minus capital Z, and image coordinate y equal to lambda times capital Z divided by lambda minus capital Z. So, as we said that the other value, that is the z coordinate in the image plane, is of no importance at this particular moment, but we will see later that when we talk about the inverse perspective transformation, when we try to map an image point to the corresponding 3D point in the 3D world, then we will make use of this particular coordinate z in the image plane as a free variable. So, now let us see that what is the corresponding inverse perspective transformation that we can have. So, as we have said that a perspective transformation maps a 3D point onto a point in the image plane. The purpose of inverse perspective transformation is just the reverse. That is, given a point in the image plane, the inverse perspective transformation or P inverse tries to find out the corresponding 3D point in the 3D world. So, for doing that, again we make use of the homogeneous coordinate system, that is the camera coordinate C or the image coordinate point C will be replaced, will be converted to the corresponding homogeneous form, which is given by C h, and the world coordinate, world point W will also be obtained in the form, in the homogeneous coordinate form W h. and we define a inverse perspective transformation P inverse, which is given by 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 1 upon lambda 1. And you can easily verify that this matrix, this transformation matrix is really an inverse of the perspective transformation matrix P, because if we multiply the perspective transformation matrix by this matrix P inverse, what we get is really an unitary matrix. Now, given this inverse perspective transformation matrix, as we said that if we assume an image point say x naught y naught, and we want to find out what is the corresponding 3D world point W to which this x naught y naught image point corresponds. So, the first step that we will do is to convert this image point x naught y naught to the corresponding homogeneous coordinate, which will be obtained as k x naught, k y naught and 0, and then the fourth component comes as k. Now, here you find that the third component or z coordinate we have taken as 0, because what we have is a point in 2 dimension, that is on the imaging plane. So, we have assumed the z coordinate to be 0. Now, if we multiply or if we transform this homogeneous coordinate k x naught, k y naught, 0 k with the inverse perspective transformation P inverse, then what we get is the homogeneous coordinate corresponding to the 3D world point, which is obtained as W h as given in this equation. W h is equal to k x naught, k y naught, 0 k. Now, from this homogeneous coordinate system, if I convert this to the Cartesian coordinate form, then the Cartesian coordinate corresponding to this homogeneous coordinate is obtained as W equal to capital X, capital Y, capital Z, which is nothing but x naught, y naught, 0. So, you find that in this particular case, the 3D world coordinate is coming as x naught, y naught, 0, which is the same point from where we have started, that is the image point from where we have started. Moreover, for all the 3D coordinate points, the z component always comes as 0. Obviously, this solution is not acceptable, because for every coordinate or for every point in the 3-dimensional world, the z coordinate cannot be 0. So, what is the problem here? If you remember the figure of imaging system that we have used, let me just redraw this particular figure. We had an imaging plane, xy plane like this, on which the camera coordinate system and the image coordinate system, camera coordinate system and the 3D world 3D coordinate system, they are perfectly aligned. So, we had this x same as capital X, we had this y same as capital Y, we had this z same as capital Z, and this is the origin of both the coordinate systems, and we had somewhere here the optical center of the lens. Now, if I take some point here, some image point here, and if I draw a line passing through this image point and the camera optical center, and the world point W comes somewhere at this location. So, we have seen in the previous figures that this point, if I call this point as C, this point C is the image point corresponding to this 3D world point W, whose coordinate is given by capital X, capital Y, capital Z, and this C in our case has a coordinate of x naught, y naught and 0. And when we have tried to map it back, this point C, to the 3D world coordinate system, what we have got is for every point W, the value of Z came out to be 0. Now, the problem that comes here is because of the fact that if I analyze this particular mapping, that is mapping of point W in the 3D world to point C in the image plane, this mapping is not a one-to-one mapping, rather it is a many-to-one mapping. So, for example, if I take any point on this particular straight line passing through the point C and the point 0 0 lambda, which is nothing but the optical center of the camera lens, then all these points on this line will be mapped to the same point C in the image plane. So, naturally, this being a many to one mapping, when I do the inverse transformation using the inverse perspective transformation matrix from image point C to the corresponding 3D world, the solution that I will get cannot be acceptable solution. So, we have to have something more in this formulation, and let us see what is that we can add over here. Now, here if I try to find out the equation of the straight line which passes through the point x naught y naught, that is the image point, and the point 0 0 lambda, that is the optical center of the camera lens, the equation of the straight line will come of this form, that is capital X equal to x naught by lambda into lambda minus capital Z, and y equal to capital Y equal to y naught by lambda into lambda minus capital Z. So, this is the equation of the straight line. So, that the points, every point in this straight line is mapped to the same point x naught y naught in the image plane. So, the inverse perspective transformation, as we have said, that it cannot give you a unique point in the 3D world, because the mapping, the perspective transformation was not an one-to-one mapping. So, by using the inverse perspective transformation, even if we can't get exactly the 3D point, but at least the inverse transformation matrix should be able to tell me that the points belonging to which particular line maps to this point x naught y naught in the image plane. So, let us see whether we can have this information at least. So, for doing this, in earlier case, when we have converted the image point x naught y naught to the homogeneous coordinate, then we have taken k x naught, k y naught, 0 and k. Now, here the z coordinate, what we will do is, instead of assuming the z coordinate to be 0, we will assume the z coordinate to be a free variable. So, in our homogeneous coordinate, we will assume the homogeneous coordinate to be a k x naught, k y naught, k z and k. Now, this point, when it is inverse transformed using the inverse transformation matrix, then what we get is the world coordinate, the world point in homogeneous coordinate system as W h is equal to P inverse C h, and in this particular case you find that this W h is obtained as k x naught, k y naught, k z by lambda plus k. So, this W h we have got in the homogeneous coordinate system. Now, what we have to do is, this homogeneous coordinate we have to convert to the Cartesian coordinate system, and as we have said earlier that for this conversion we have to divide all the components with the last component. So, in this case k x naught, k y naught and k z, all of them will be divided by k z by lambda plus k. So, after doing this division operation, what I get in the Cartesian coordinate system is W equal to, sorry, here it is not C, it should be W. So, W equal to x y z, which is equal to, so this point should be W. So, what we get is W equal to x y z, which is equal to lambda x naught divided by lambda plus z, lambda y naught divided by lambda plus z and lambda z divided by lambda plus z. So, on the right hand side all the z's are the lowercase letters, which is the free variable that we have assumed that we have used for the image coordinate, and for the matrix, the column matrix on the left hand side, all x, y, z are in the uppercase letters, which indicates that these x, y, z are the 3D coordinate. So, now what we do is we try to solve for the values of capital X and capital Y. So, just from this previous matrix you find that the capital X is given by lambda x naught divided by lambda plus lowercase z, capital Y is given by lambda y naught divided by lambda plus lowercase z, and capital Z is equal to lambda lowercase z divided by lambda plus lowercase z. So, from these three equations I can obtain capital X equal to x naught by lambda into lambda minus z, and capital Y equal to y naught by lambda into lambda minus z. So, if you recall the equation of the straight line that passes through x naught, y naught and 0 0 lambda, you find that the equation of the straight line was exactly this, that is capital X equal to x naught by lambda into lambda minus z, capital Z, and capital Y equal to y naught by lambda into lambda minus capital Z. So, by using this inverse perspective transformation, we have not been able to identify the 3D world point, which is of course not possible, but we have been able to identify the equation of the straight line, so that the points on this straight line maps to the image point x naught, y naught in the image plane. And now, if I want to exactly find out a particular 3D point to which this image point x naught, y naught corresponds, then I need some more information. So, for example, I at least need to know what is the z coordinate value of the particular 3D point w. And once we know this, then using the perspective transformation along with this information of the z coordinate value, we can exactly identify the point w which maps to point x naught, y naught in the image plane. Thank you.